sort of the setup. And the thing is that we're going to have, a nice way to think about control is through optimization. It's a way to synthesize, a way to think about constructing policy. So optimization is a route to policy synthesis. And again, that's sort of my view. I mean, that it's really artificial often when you come up with this cost function. It's not God-given. This thing here is often very approximate. And based on that, mainly this is a way to come up with a candidate set of policies. So basically, what we did last time is we built up the tools we need to be able to think about this. And I hope to God by the time the course is over, you don't think it was a waste of time. We're going to be using all these techniques a lot. So, I mean, I'll explain today. We're going to move today. I'm going to go through and cover a lot of ground because it's basically almost identical to what we were doing in the last few lectures. There was a Poisson equation before. Well, now it's a controlled Poisson equation. And I'll explain what it means. Before I do that, just one final comment on Markov stuff. So I was just explaining, what control is all about. But, there's like 15 pages on Perron-Frobenius theory in those notes I told you not to read, all right? But I realized that in the next homework assignments, you're going to need to compute like the invariant measure, invariant probability mass function and stuff like that. So there's one trick you should all know. There's one trick that's so cute. So just take a finite state space. Just here's an example. Okay, and you can imagine to be able to use this for Poisson's equation, all sorts of things as well. You can read that in those notes. But because you're going to want to code this, I want to show you a trick for solving this equation. In MATLAB, you'd say, oh, well, it's an eigenvector. I'll compute all the eigenvectors of P, and I'll find the one corresponding to eigenvalue, or P transpose. Pi is a row vector here. So it's pi is a member of an eigenvalue of P transpose, or pi transpose if you like. Pi is a row vector, pi transpose is a column vector. So if you've got, a million states, maybe you can do it, But don't, just like I said, don't ever invert a matrix in MATLAB. There's better ways to do it typically. There's such a cute trick to solve this equation. So this is an eigenvector problem, but it can be converted to an inverse problem in a really clever way. So here's the genius of Perron-Frobenius. Okay, so choose a function S and assume nu is a probability mass function. It's easy to do this. I mean, this is just a big matrix, right? Just take one positive element and choose S to be all zeros except for that element for X, and the X that's a row and that's a column, and nu to be all zeros except for at the X prime where it's positive. I mean, it's trivial to do this. Okay, I'll make you do it in the homework. All right. So then what you can do then is the way you write this down in the notes is P is greater than or equal to S cross nu. And what does that mean? S, remember functions are column vectors, and probability math functions are row vectors. So this cross is just to emphasize it's an outer product. All right, it's just, just to remind you. And what you do is you just subtract it from both sides. So basically, P is greater than or equal to a rank 1 matrix. This is the one genius step in Frobenius theory, and everything else follows. And an example is to solve this equation. I'd write pi minus S cross nu, pi times P minus S cross nu equals pi. No, it isn't. Minus something, right? Minus delta nu. What's delta? Now remember, S is a column vector, nu is a row vector. We just subtracted off a rank 1 matrix. And if pi is a row vector, I multiply it through, the row vector hits the column vector, wham, it's a dot product. So delta is nothing but pi dot S. Which is unknown, but you'll see it doesn't matter. So what happens is that we can flip this around, and what do we get? I'm going to put this on this side and this on this side, just shuffle things around. Do you agree with that? I took this to the right-hand side. I took the delta nu to the other side. I flipped it around the blackboard, spun it around. These equations are identical. Okay? Delta nu, I just, check it out. It's the same thing. So we've got a representation for pi. Oops. Ta-da! So in MATLAB, you can do this in one stroke. Did I get that right? Yeah. I just multiply by the inverse on both sides. Hold on a second. In MATLAB, in one stroke, you don't invert this matrix. You do that slash command. You've got S, you got nu, go slash, you got this thing. What's the objection? I heard an objection. Yeah, what's the objection?
Delta.
Well, you know delta, because you see, once you compute this guy, that's a constant. I know how to renormalize. See, I know that pi sums to 1. So I sum both sides over 1, and I get delta. Isn't that cool? So basically, just one matrix inversion, not matrix inversion, one slash command in MATLAB. You've got pi, but unnormalized, right? Basically, what this is it's a left eigenvector, but not normalized to sum to 1. But you just to find delta, you sum both sides. This summed over x is 1. This sum to x is obviously 1 over delta.
How do you think mu?
Any way you want. You just have to make sure, as long as this inequality holds, and these guys are both not identically 0. This is positive for some x, and that's positive for some x. They both have to be non-negative as well. Then, the theory, I think the theory that those notes is complete. It explains it exactly. And because what you can do is you can show this exists as a power series expansion. There's a really beautiful proof of that. It's incredibly amazing. That you can get so much for nothing. So if you ever have to compute pi, which you will in homework, do that. Yeah.
You think that delta is pi
No, this just means that it just is, so remember this is a matrix, where x corresponds to the, rows. Say x is an integer of 1 to n. That's the, the xth row, the xth column, right? And this is saying it's greater than or equal to a matrix that's of a product form, a column vector times a row vector. That's what I mean by this. It's just fancy notation so you don't forget that you're talking about an outer product, not an inner product.
No, I mean, I was talking about delta.
Oh, but delta turns out to be pi of s, which you don't know. But once you have this expression, you know it because you sum both sides over x. Remember, the sum over x of pi of x equals 1. All right? This is a row vector which you can compute instantly. Sum this over x, you get 1. Sum this over x, you get delta times whatever the hell that is. You just compute it in MATLAB. So the sum of this over x is delta inverse. So you got delta.
And this is for when you already have pi?
No. This is a constructive thing. I'm saying I'd like to solve this equation. I go through and say, well, I'm going to try to solve this equation instead. And there's two unknowns. There's delta, which I don't know, and pi. All right? So I go through this magic, and I say, well, pi is equal to this. So what I get is I get pi is proportional to this row vector is proportional to this row vector. What's the proportionality constant? Well, shit, you just use this fact.
So will you tell me is that this that inverse matrix, that's going to be a function of x?
Yeah, this is a matrix, that's a row vector.
Okay.
Just like here, I have a matrix times a row vector, I get a row vector. Yeah.
This applies for infinite dimensional.
Yeah, well, the thing is for analysis, it applies to general state space Markov chains. But fuck that, excuse my language. Thank you for turning up the volume. It's a great, it's the best computational tool. If you want to compute the solution to this, the only way I know how to do it is this.
So how do you put an infinite dimensional matrix in that?
No, that's for analysis. No, I'm talking about for computational methods. I'm talking about for finite states of Markov chain. You can solve this with, I don't know, 100,000 states, 1 million states. If you use the slash command, you can't invert this if it's 10,000 by 10,000. With the slash command, you can. And it's the only method I know how to do it. Can you imagine if you had to compute all eigenvectors of P?
So in MATLAB, essentially what we would have is we would have pi equals.
No, you would compute this.
And delta would be 1 over some delta.
Yep, exactly. You got it. Okay, so that's given in the notes. So, all right. So this was one thing that I knew you'd need, and it needs to be explained.
Delta is not the normalizing constant.
Yeah, just delta is just a normalizing constant. That's why I'm not bothering to write it down. If I tell you pi is proportional to this row vector, well, you know how to normalize. You just have to make sure that pi sums to 1.
So
the same thing comes in the homework as well, the first problem in the homework.
Isn't it difficult to choose an S and a V?
Anything works. No. Anything works. Yeah.
So different S and V's would probably just give you a different normalizing constant.
Well, for example, I guess I'll erase this. Yeah, you'll get different normalizing constants. I mean, if you make S and nu very small, see if this was 0, that's not invertible because pi is an eigenvalue at 1. Therefore, if S and nu are very small, this will be very ill-conditioned, this inverse problem. So you'd like S and nu to be as big as possible. But one example, take S to be 1 at a particular point and 0 everywhere else. So then it's very easy to get a lower bound because you only have to get the lower bound at 1 point. And what would you take for nu of x prime? Well, I want this lower bound to hold for all x, but this is 0 except at x equals x dot. Well, why not just make it equality there? There's one example. So that's a tight example, because it's exact at one point. And so that's what I would recommend, but yeah.
So you're just taking one row out of the P matrix and making that.
Yeah, you're just knocking out a row, exactly. You got it. Yeah. You're knocking a row out of the matrix. Yeah, so, Oh, well. I don't know, that's too hard to say. Forget it. It's too hard to say. I'd have to put it next to. There you go. So you're just killing off a row. Yeah. All right. What's that? It doesn't have to be. It doesn't have to be. There's nice interpretation. In the notes, I made it a PMF. The only thing that's crucial is that these are non-negative. And the reason that that's true is that then you can justify this being a power series expansion. It becomes well-defined. I mean, well, no, there's more than that. There's lots of reasons why it has to be non-negative. Yeah. All right. So, yeah. So, all right. Done with that. All right, so we're going to, here's the setup. We've got again, X is a state space. Again, I don't know how to write grand U's on a blackboard, but in an operations research course, this is called an action space. For control audience, it's an input space, a set of possible inputs. We have a control transition matrix, but before I get to that, we're going to have we have causal inputs. So U of t. So I already kind of gave you an example of that, where U is a function of X, it's causal, is a causal function of the X's. So I already said that, but sometimes we have to, when we get into the sort of the learning part of the course, we have to make phi also a function of some randomness outside. But we'll wait on that. For now, we'll just assume this, that U of t is some deterministic function of present and past state values. In the end, we'll get rid of the t, we'll get rid of this. It'll be a stationary policy. A stationary, what they call a stationary deterministic policy is state feedback. Okay, my input at time t is a static function of my current state, period. It's a state feedback. And we all know that's a pretty strong assumption you can measure the state. And what do people do in practice is they come up with approximate models where they can observe the state. They do all sorts of hacks in practice. Being able to, I mean, if you have a really accurate model of a system, the state is probably something crazy, you know, and it's way too big and complicated. So we often use approximate models. Right? So I can say all this without even talking about dynamics or anything. This is just how you think about control, full state control. But then, you know, we have dynamics. So now I have to look at the probability that in one step in the future, I'm at state x prime, given measurements of all the past states, all the past actions or inputs. And I'll put a little semicolon here. Okay. You know, so a conditional probability is always a function of the observations. And I'm just saying, well, you know, hey, we happen to see x and u. This will be only a function of these two guys. So I don't need, given the current input and the current state, I don't need the past information. And then, you know, so that's, so that's the definition of a controlled Markov chain. And then we're going to, of course, have some notation for this. And it's not perfect, but I'm just going to use a subscript. You know, that the probability of going from x to x prime, given the current input is u. That's the notation I'll use. Okay, so this is one notation and two, time homogeneity. The fact that this doesn't depend on time. You know, you could imagine something where, you know, depending on whether it's nighttime or daytime, the dynamics change. But we'll look at a time homogeneous model. All right, so live with it. We have a controlled transition matrix, and all that funky notation I talked about before we're going to start using again. So you never liked pH? Well, too bad. You're going to get it even worse now. So what do I mean by PUH? You know, for fixed U, that's a matrix. Or you can think about this as a really, well, it would be a very tall matrix because the rows are x's and u's in a way. You know, but forget that. For each U, it's a matrix, a square matrix. So exactly the same notation. All right, so you know you're like I said before, we're going to keep using this throughout the course. You gotta know what I mean when I write pH and now p sub UH. All right, okay, so that's a controlled Markov chain, and then you stick a cost function. Well, you could. It's actually easier to think of it as a two-dimensional matrix, really, you know, where you enumerate all the x's and u's for rows. It actually, we'll see. It's more useful to think of it that way. It's, you know, it could also be thought of as a cube. You're right. Yeah. All right. So we're going to have a cost function, you know, like we had before, but now it depends on states and inputs. And forget it, I'm a control person. I'm going to put the damn plus sign there, okay? So it's a positive value. It's a cost function. It's not really essential, but you know, we'll assume that. So you know, it's a function, a real valued function of states and actions. Another way to say that is it maps x cross u to r, but we might as well make it non-negative. So now it's an MDP. Markov decision process, another ugly term that was given to us by the operations research community. Thanks for turning off the volume there. Because damn it, it's just, I don't know why we let computer science and operations research steal this field from us. This is control. It's a state feedback, you know, I mean, it's nothing but, you know, but we were co-opted when we weren't looking back in the day. But the EC, I mean, the control people made the biggest contributions to this, damn it. Okay, so it's an MDP. And there's a whole bunch of cost criterions we'd look at. One might be average cost. Okay, and it makes me uncomfortable not to put a soup there because the limit might not exist. But under the policies we look at, it will exist. So, and it makes me uncomfortable not mentioning the initial condition here, but under the conditions we'll impose, it doesn't depend on the initial condition. It's deterministic, it's a number. We're going to construct it. We could do it by the end of today if we wanted to, but let's not, let's wait. But we'll have a formula for eta star, basically. So this looks effing scary, right? I mean, I have a sample path limit here, and I want to minimize over all inputs, you know? Well, we'll see. I will show you that it'll become trivial in just a moment. Right? So if this was a MDP course in operations research, they would probably not even mention this, and they would talk about discounted horizon optimal control. Okay, so you look at the cost, the expected cost at time t. So here there was no expectation. I could have put it in, but I left it out for now. And then instead you have discounting level t. And at this point, some in operations research would love to say, that's a joke, in the long run we're all dead. So that's a quote of Keynes, you know, an economist. It's nonsense, nonsense. This is much more robust when we solve this problem than this. The policy we get from this, you know, very often you can get examples where it's not stable, Here it always will be stable, you know. And we can get transient as well as steady state bounds. So it's just complete propaganda. It's a lack of understanding that people think that we'll only care about the infinite horizon limit. You know, the solution to this problem takes into account both transient and steady state performance. You know, yeah. And I'm going to clarify that. So. So,
Expectations question.
yeah.
Is that the expectation times beta to the t or raised to the beta to the t?
No, beta is less than 1. And I should say greater than 0. And that's the discount factor, you know. So we're just taking this expectation and then discounting it by a factor, you know, beta to the t. So it's a product there.
That's a product.
Yeah, this is a product. It is just a scalar, and that's an expectation. That's it. Now it turns out that it looks like total cost, but you can make it much more crisp. Well, no, let's do it first. You guys can handle this. And by the way, just like before, I don't want to have to keep writing given x of 0 equals x. I'm going to write e sub x, okay? So does this look familiar? So c tilde will be c minus eta star. That's called the relative value function. Okay. The solution to this optimization, this total cost, so there's a total cost until extinction. You basically, and yeah, tau is before. You take some distinguished state and you look at the first time, the first entrance time to that set. So minimum of t equal to 1, x of t equals x dot, no change at all. So remember, this was the solution to Poisson's equation when we didn't have a control. You know, we didn't have a minimization here. It wasn't eta star, it was eta, it was the mean of c. Well, it's just a very simple generalization. So the solution to this minimization problem is exactly the same as the solution to that minimization problem. Okay? And, well, we'll see a lot more. And it gives you the optimal policy. Do I have to write this down? See the notes. I don't have to write it down. Is that clear? Okay, so if I solve this, I'll write it down. So solution not that hard. All right? And the thing is that this looks so off there. I mean, this is so strange. A sample path limit, blah, blah, blah. This is much more concrete, except we don't yet know what eta star is. All right? But this will give us a dynamic programming equation. Well, that apparently doesn't, you know. And again, it's a total cost in a sense, very much like what we saw in the finite, you know, for uncontrolled Markov chains. You know, it should look familiar to you, right? And two, you can construct a random time so that this minimization problem is the same as this. And what kind of random time is it? It's just geometric, you know, basically that's it, you know. So So it's sort of a joke. And basically, I take a geometrically distributed random variable, completely independent of everything else, and it has parameter beta. So this probability, so to be a geometrically distributed random variable means this is equal to this for some beta. Well, I'll choose the same beta. And so by independence, I can take that beta t inside and replace that by that. And I'll let you do the work. You'll get this, okay? All right. It's just a way to think about this. It's just a way to think about this. In this case, I'm looking at some large, if beta is close to 1, a large time, random in the future, and looking at total cost. And in this case, I have to look at tau, and it wouldn't have to be the first hitting time. It could be the second, the third, the fifth, the billionth, just like I talked about before. But some time distant in the future, possibly. But I have to look at the relative cost instead of the cost here. All right.
Why did you rewrite number 2? Is it just to show that they're equivalent?
It's a conceptualization. When you want to try to solve these problems, it really helps to be able to have a way of thinking about them. You know, and I'm going to give an example today where knowing that it's like a total cost is useful. I think this is a little harder. I mean, if beta is close to 1, then t is practically infinity, and you're just looking at like total cost, like you wouldn't deterministic control very often. If this point x dot is like the origin or something, we're in Rn, you know, this is like the cost to reach the smallest state in the state space. It's just the mentality you have in deterministic control all the time. You know, once you have that intuition, it gives you ways to cook up approximate value functions, because we rarely can compute these exactly. You know, this is essential to. I mean, once we have this, we have the optimal policy. You know, but we'll never compute these in any problem you care about. You know, so we're going to have approximate methods. You know, deterministic nonlinear control is almost always intractable, and stochastic is just as bad, no better, no worse. You know. People tend to think it's worse. I don't agree. I don't.
So you have to generate different geometric random variables in there.
Well, no. This is just no. I wouldn't use this for computation. It's a way to think about it. You could, though. I mean, you could use this for a simulation-based algorithm for sure. Because I mean, the fact that that is an infinite time horizon. If you're going to blindly use some simulation-based method to estimate this, you know, it'd be annoying. It might be much nicer to generate IID. Samples of geometric random variables, and then you can estimate. You can get an unbiased estimator of this. That's right. You could use it for computation. All right, but I was thinking just conceptual.
That will also,
Yeah.
I mean, that will become 0 when t goes to, t becomes larger and larger.
Yeah, that's right. I mean, you could settle with that too. You could say, I'm happy with a bias of so much, and take a fixed time horizon and accept some bias. And whether that's better than doing that, I don't know. Yeah. Okay, so we have our beloved principle of optimality. I can go through this fast since we've sort of done it before. Let's do it for discounted cost. All right. So, remember before in the deterministic case it was really simple. I start here, I've got an optimal path. I take that optimal path. I get to here. What am I going to do? I'm going to continue to follow the path. And what that says is that from this point, the cost to go is easily computed, and the path to go is easily computed. It's just what you would have done. Your plan is still the same. In the stochastic case, of course, it's a bit trickier, but not that much trickier. You just break up this sum. So it's a minimum of all u's, and you just isolate u0, and then look at the remaining u's. So I take the 0th term, beta to the 0th 1, and this is just c of xu, u of 0, I'll call it u. So that's the first term here. And then I have a sum from 1 to infinity. Okay, I've just rewritten this down, and I've just saying I can do this sort of minimize this, and then minimize over u. Okay, so I can minimize all the other u's first, essentially, and then minimize over u of 0. All right, and then I can pull out my transition matrix. So all I've done, so here I was minimizing over all of ut, u0, u1, all giant input sequences. Here I'm sort of doing it in order. I'm taking, first of all, I can take the min outside if you like. But this doesn't depend on the future u's. So I could bring it over here. Yeah. Oh, minimum of all. I just don't know how to write down infinite sequence. So it's u of 1, u of 2, u of 3. It's the same as this, right? Except that I'm throwing away u0. Yeah.
So you say u1 infinity?
That's just one way to do it. It's a typical. It's a common way of writing down a sequence. Yeah. What I mean by this.
Just write u3 because t equals 1 to infinity.
U of 1, U of 2. This is just shorthand for having to write out this whole thing. Okay. All right, no problem. No.
With U of S instead of the squiggle.
Yeah. Oh, yeah. Okay. Yeah. That's true. That might be more. Yeah, but yeah, both are valid. Okay, so now we got to bring out our transition matrix. It's really annoying, but let's do it. I'm going to save chalk by continuing with the U1 to infinity. Let's see. Okay, so I'm basically going to look at all possible locations I might be in one step from now. You know? And looking at this expectation, you know, given that I started there. What's that? I'm not done. Hold on. I'm not done yet. Right? Wait. All right. So I'm looking at all possible values I can be at time 1. And so I've got. Hold on a second. Let me write it down, and then we'll stare at it. There. So what's your question?
Not sure now.
X1 equal to X prime.
I'm trying to absorb it all.
Yeah, no, I know. I'll slow down. So this was a definition, really. I mean, I just went and decomposed it a bit. And then I'm saying that x of 1, you know, given I started at x, I can take on various values with that probability. You know, x prime is a value, possible values of x of 1.
I think maybe we were expecting to see the PU times the cost.
Yeah, that's what I was
It's right there, the cost. No, it's same there. Oh, I just brought it down.
No,
This and this are identical.
Another expected value.
Yeah.
But I think.
Oh, it definitely has to be.
I thought the expected value was the probability function.
Well, the only thing I wish I had done is I wish I had swapped out the sum over time here, but I'll do that in a minute.
Why isn't it not just the PU times the cost function as opposed to? I thought the expected value was defined as.
This is just a one-step transition matrix. I mean, right here, I'm looking at the expectation starting at x of 0 equals x, all right? And all I'm doing is I'm saying, well, that expectation, I can look at the expectation given that I started, that at time 1 I'm at x prime. But I have to look at all possible values of x prime and sum over the probability of being there. That's all. Yeah. There's an expectation at time t, so is this. I'm just breaking it down. All right. But I really want to swap out that sum and min. So this guy's adapted. So whatever x prime that is, it has to depend on it. So I can take this whole thing out. I can swap everything out. I can do anything. Oh, wait. Let's do this carefully. Hold on. I almost slipped up.
Pull the sum of P.
Oh, it's something. Yeah, that's right. So it's the sum over x prime. In fact, I'm going to take a beta out. I'm going to take one of these betas out, and make that beta t minus 1.
min?
I just want, I've got my notes there, but I want to, it's good for me to slow down, and it's also good for you to guess what I'm about to do.
I think you're going to write min.
What's that?
I think you're going to write min.
Oh, I'm definitely going to write min. I need that min. Oh, I'll do it for you.
Thank you. That's all I want.
Well, it's also good for you to guess what I'm going to do and then do it. But I've got the sum. I've got that. Oh, I'll keep it as 1.
So hold on. What happened with the beta?
Hmm?
Oh, you just took out 1.
And now we stare at that. And remember about this time homogeneity, okay? Basically, the dynamics don't change with time. So if I start at time 1 and look at the total cost to go, from x prime, it's the same as starting from 0 at the same state x prime. So what is this monster minimum? It's 8 star, yeah, beta, because that is it's going from 1 to infinity, so it's beta 0, beta 1, beta 2, so it's the right sequence of discount factors, and this is the cost, t minus 1 steps ahead, given I started x prime. So there you have it. All right.
What's DCOE?
Yeah, I was about to say it. So the discounted cost optimality equation. Okay. All right. And so there it is.
Optimality equation?
The optimality equation. So the discounted cost optimality equation. So this thing here is obtained by something that looks sort of like our Poisson equation, but it's got a discount factor beta there. Yeah, and a minimization.
How do you transition from x prime to x, like in the second part?
Well, right here, I mean, if you think about it, what is this expectation? It's the expectation t minus 1 steps in the future of the cost, given I started at x prime. Forget it, let's just start anew at 1. At time 1, I'm at x prime, and t minus 1 steps later, I'm looking at the expected cost. I'm multiplying that by beta to the t minus 1, and something from 1 to infinity. That's basically that definition. It really is. What was the question again?
It's x prime.
So the reason is because there's a sum over x prime, but
Yeah.
then you add that specific
Yeah.
it's the matrix.
Yeah.
Yeah. So here's that compact notation that I'm forcing you to. This whole monster is 8 star beta of x prime.
Yeah, that's what I mean. Because it was a sum identity.
So this whole crazy sum is just with the minimum. The whole thing in brackets is 8 star of x prime, but then I'm matrix vector multiplication. All right. Yeah. Okay. So there's the discounted cost optimality equation, and because there's a minimum, it makes it a bit hard to solve. But we've got a whole bunch of ways to solve it. So, yeah.
So that at the bottom there is h beta star of x prime.
No. Don't forget our notation. When I wrote it down. I'll write it down again. When I write down pu h of x, I mean the summation over x prime, pu x to x prime, h of x prime. Okay? So this is the thing I said, it was up here a moment ago. You know, I'm going to make you, you know, I'm forcing you to use this because I don't want to have to keep on writing sums in situations like this. You know, it's really, really tedious. All right? And so you can imagine what happens in the stochastic case. I mean, the average cost case. What's that? I'm not going to derive it. You can go through the same arguments. You know, I wrote in that relative value function. It's the same equation almost. But any more questions on this derivation? You do need to know it. Not for this exam, but the next one. You don't need to know it for this coming exam, but you definitely need to understand this thing. All right? So we can take a guess at it. What will the average cost optimality equation be? I say it's the same thing. There's no beta though. So that relative value function that I wrote down before, you can go through and actually use the same set of arguments. I know it's a bit weirder looking because it's a random stopping time. I mean, here we didn't have that. Here we had a deterministic sum, and there we would have a random final time. But that was why I derived Poisson's equation with that representation. Okay, so I'm not going to do it in the controlled case. I showed you one representation of Poisson's equation in terms of an expected sum to a hitting time. You know, I'm not going to do it again. So using the exact same arguments, you can derive this this equation for that relative value function I wrote down. It's a solution to this equation. And the reason there's an eta star there is if you subtract it over, you'll get the c tilde that I had before, c minus eta star. Yeah. All right, so it looks like Poisson's equation, and it is. If you plug in the minimizer, you'll get Poisson's equation for a particular policy. All right, so I was hoping to do that. Just blast you with it. Just here's a cost criterion, here's a model, and here are the two dynamic programming equations we'd have to solve. And you can imagine you can't do it very easily very often. We'll take a break in a second. I just want to say a couple of things. Where are we going to go with this? Okay, so this value iteration algorithm that we looked at last week, it applies to either one of these problems exactly the same. And the analysis of value iteration is identical almost to what I showed you before. Okay, you can even use coupling.